For our next session, I would like to invite Dr. Robert Knight, who's a neurologist who joined UC Berkeley in 1998 to lead a new initiative in human neuroscience. Dr. Knight received BS in physics from Illinois Institute of Technology and MD from Northwestern University. After his MD, he did his neurology residency at UCSD. So we have a lot of representation from UCSD here today. And he also did his postdoctoral training at the Salk Institute. During this time, he received the Jacob Javits Neuroscience Investigator Award from the National Institute of Neurological Disorders and Stroke. He is currently Ivan Rauch Professor of Neuroscience, and is also the director of the Helen Wills Neuroscience Institute at UC Berkeley. Please join me in welcoming Dr. Robert Knight.
Thank you, Dharmendra. Well, it's a pleasure for me to be here and to introduce Jeff. His accomplishments are clearly laid out in that summary that IBM provided for you, with his early involvement with grid electronics and his election to the National Academy of Engineering in 2003. I thought I'd just give you a little bit of my personal insights into Jeff. I met him in, I think, late 2001, and I wasn't quite sure how the conversation would go, but it was very exciting for me that I realized that we shared the same language, because he was extremely conversant in neuroscience, in anatomy and physiology, and we really had a very interesting time, I think, in that first discussion, talking about thalamocortical loops. Jeff took his deep interest in neuroscience and used it to form the Redwood Neuroscience Institute in 2002, which really immediately attracted a nice cadre of young and even more senior scientists interested in computational and theoretical neuroscience, and became a very vibrant intellectual site in the Northern California Bay Area. Luckily, I guess for Berkeley, Jeff had yet another idea for a company, and the company is actually based on his model of cortical function that he's going to present today, and I'll let him do that. And last year, he actually moved his Redwood Neuroscience Institute to Berkeley, where it reemerged or reformed as the Redwood Center for Theoretical Neuroscience. Now, I'm happy to report that we have a new director, Bruno. Are you here, Bruno? Where are you? Somewhere. Bruno Oshausen, and we've already, in a year, Bruno's already feeling the pressure of having not enough space and too many people interested in this burgeoning area. So that's a bad problem for him, but I see it as a good problem. It means there's a tremendous amount of interest in this very important area of neuroscience. So I think I'll close with just a couple. Context has been a theme here, and I think Dr. Edelman really made a strong point that context determines a lot of things that you say, do, or believe, and I'll give you a very short example of that. I could think that, I'm the director of neuroscience at Berkeley, and Jeff was really the impetus for forming theoretical neuroscience at Berkeley. So here's the sentence: I've got Jeff in my pocket. Now that would be pretty stupid, because he's not in any pocket. But on the other hand, I could have the same. I could put my hand in my pocket and I say, wait, I do have Jeff in my pocket, because as many of you do. So context really is everything. And with that, I will turn over the podium to my friend and colleague, Jeff Hawkins.
Thank you. Is my mic on? Everyone hear me fine? So just in case some of you don't know who I am, and I've had two lives, you'll have to fill in a couple pieces here. I've had a lifelong interest in neuroscience and been pursuing it very, very actively for a number of years, but perhaps better known in the world of computing, which is I was the founder of Palm Computing, and I'm still involved with that company, and so the architect of the Trio and the Palm Pilot and so on. But we're here to talk about cognitive computing today. And I took the initiative of saying, well, I'm not going to do a neuroscience talk. I've done a lot of those over the years. I'm going to do a cognitive computing talk, so it's going to be a bit more engineering-oriented. So the gentleman asked the question last time, how would I build something like this? I'm going to talk about that. I'm going to start with a little story, though. I'm going to start a story from my computer life. Palm Computing was started in 1992. And right around that time, there's a lot of interest in mobile computing. And the CEO of Apple, John Sculley, once got up and said, this is the mother of all markets. And he was really excited about this future mobile computing market. He was thinking of the Newton, for example. And then the CEO of Intel, Andy Grove, heard that comment and thought John Sculley was full of it. And he said, that's a pipe dream driven by greed. So we had this little startup company called Palm. We had a dozen employees. And we had one major CEO of one major company saying this is the mother of all markets. And then we had another CEO saying this is a pipe dream driven by greed. So one of our employees made this little spinner. I don't have an actual picture of it. But this was placed on the wall, so when you enter our office, you could spin this every morning to see how you should feel about your work that day. Now, it looked like Andy Grove was right, because the Newton was a big failure, and there was all these failures in the mobile computing space. But then, people started having success, including myself and Palm. We had the Palm Pilot, and now if you consider mobile computing as a cell phone and so on, maybe it is the mother of all markets. So that was an interesting turn of events. I think we could have a similar little spinner today. This would be today's cognitive computing indicator. Now notice the arrow is just indecisive at this point in time, but not in your lifetime or any moment now. Now I'm going to make the case for both of these. I'm going to walk through them right at the moment. Let's first make the case for not in your lifetime. There's a lot of reasons you might think it's not in your lifetime. First of all, people have been trying to do this for a long time. So I'm going to paint with a very broad brush right here, so I don't want to insult anyone. But we've been trying to do this for something like 50 or 60 years, 5 or 6 decades, under the various monikers of AI, neural networks, variations like called fuzzy logic. These are all things that had their conferences, their days, their big moments in the sun. Do you remember, some of you are old enough, the 5th generation computing project came out of Japan? This was, there's a few people old enough to remember this. I mean, this had Congress shaking in their boots, because Japan said, we're going to build intelligent machines, and we said, oh my gosh, the US has lost its technical competency, we're going to be behind. Then last in the 1990s were the decade of the brain. Well, not a computational thing, it was certainly a neuroscience thing. And these are all good things, people really worked hard at it. But reality is we haven't had much success. And people have been saying this and talking about it for a long, long time, and we really haven't much success. Today, there is no machine on this planet that you can show it a picture of something and say, what is it? That is something you and I find really easy to do. And we do it really fast. There's no machine that can do that. I will argue, and despite what the previous speaker said, there's no machine today that really understands language. There's recognition, there's various prediction things, but no machine that really understands language like you and I do. There are no real robotics. The great effort shown by Professor Dr. Edelman this morning, that is not a really flexible robot. That's not walking around serving you breakfast, okay? We really have not made a lot of progress. We've made a lot of progress, but in some sense we haven't really made our goals at all. And then people say, well, you know what? It's going to be really, really hard to solve a problem because the brain is so complex. And the great talk this morning by Markham says, it shows how complex that thing is. And this has been known for 100 years back to Cahal. But I often hear people say, well, the brain's the most complex thing in the universe, which is really a hubris to say that. How do we know that? Who knows? 30 billion neurons, okay, it's complex, but maybe there's some structure there and so on. Who knows? But anyway, these are the arguments for people to say, why do you waste in your time trying to do this? On the other side of the fence, I can put some good arguments for why we should be able to make progress. Let's just talk about the neocortex. Of course, that's the part of the brain we're interested in here. I'm going to say the neocortex is really, really fast. Now, why do I say it's fast? It's because it's made of very slow elements. So a neuron can basically do a computation in about 5 milliseconds. And you can do sophisticated cognitive tasks, such as recognizing a picture, in well under half a second. So there's something called the 100-step rule that basically says the brain solves in 100 neuron-to-neuron transitions what we haven't been able to do with the biggest computers in the world. And you say, oh, yeah, but there's a lot of neurons going at once. But still, it's fast. It is really fast. It solves these problems very, very quickly, given how slow it is. The other thing is it's extremely flexible. When you're born, your neocortex doesn't know anything. It doesn't know about buildings and computers and projectors and PowerPoint, and it doesn't know any particular language. Maybe it still doesn't know about PowerPoint. That's what I'm hearing out there. I don't know about PowerPoint, but some people do. But you can or you cannot learn a language. You don't have to learn a language, but most people do. And you can learn one of 1,000,000 spoken languages. You can learn written language or spoken language. You can learn sign language. You can learn the language of mathematics, the language of physics, the language of music. These are all languages. And you can learn any one of these or none of them. we can live in any kind of environment. This is the most amazingly flexible piece of tissue that anyone's ever conceived of. And it can do all these things. That flexibility speaks to simplicity, not to complexity. It means that there's got to be some principles that are pretty basic running in this thing that allow it to do this stuff. Third, it is extremely robust. We are losing neurons all the time. It does affect us slowly when you get to my age, but generally you can still think. And the brain is very robust to trauma, and certainly in some places and not in others. But even think about someone who loses vision. If you lose all your vision, you become blind. You still understand language. You still build a model of the world. Helen Keller, who couldn't hear or see, had the same model of the world that you and I have. That is incredible robustness and flexibility in the system. Now, we do have, as you heard, we have a tremendous corpus of data about brains. We know tremendous about the anatomy of the brain and the physiology of the brain. And you can, as I have, you can try to piece this together. You can try to really work on all the subsections, try to say, what do we know about their connectivities? What do we know about the layers and the cell types? You saw some of that this morning. And we also have a lot of mathematical tools that we didn't have. And you'll see some of those in my talk here that we didn't have a long time ago. We have a lot to work on here. We have a lot of the pieces of this puzzle. We have a puzzle which seems like so complex, yet somehow it's really simple. And we just need to think about it. And the last piece that came up, this is an idea that was proposed first time 27 years ago by Vernon Mountcastle, the famous physiologist. He made the observation that although the neocortex, it does all these different things in different areas. There's vision areas and hearing areas and areas that play chess and areas that play, do this and that. But it looks like it's built on a common algorithm. That is, everywhere you look, and you saw that in some of the slides this morning, everywhere you look, looks like a similar structure. There's these similar layers, similar cell types. They have similar connectivity patterns, and so on. And his conjecture was the way the brain does vision is the same way it does hearing. It's the same way it does touch. It's the same way it does mathematics. It's the same way it plays Scrabble. It's all the same thing. And it's the same way it does motor control. That there's a common cortical algorithm. Now, I have personally asked several hundred neuroscientists over my career whether they believe this or not. And based on that sample, about half of them do, that there's a common cortical algorithm. And the other half is kind of split between people who either don't believe it or, believe it or not, don't know about it. This, to me, was one of the most major discoveries in neuroscience at all times, that there's a common cortical algorithm underlying all these different processes. So that gives us a target. We don't want to solve language. We don't want to solve vision. We want to solve something that is uber to that, something that is more fundamental to that. And that's been sort of the genesis of my work. Now, I have a theory about how the cortex works. I'm going to tell you about it. I'm going to tell you how we're implementing it and what we're doing with it. Part of this theory was published in a book that came out a year and a half ago that I wrote with co-author Sandra Blakesley called On Intelligence. That was more of a overall top-down description of what intelligence is and how the cortex works in biological terms. Since that book was written, a lot of progress has been made on this theory. A lot of it due to my colleague Dilip George, who's in the audience here, which is sort of basically a mathematical formalism for that theory. And I'm going to be telling you about here today. I'm not going to give the biological mapping of this theory today. I chose to talk about cognitive computing, not a biological theory, although I can pull me aside later and I can give you a very, very detailed mapping between the theory I'm going to tell you and the biological anatomy and physiological properties of the cortex and thalamus. Okay, so let's get into it here. I'm going to frame the problem. Here is the picture that sort of frames the problem. On the left, we have the world. The world has things in it. There are physical things such as people, cars, and buildings, and chairs, and so on. There are things in the world which don't have a physical presence in that same way, things like words, songs, and ideas. These are structures in the world. They exist out there. On the right-hand side, we have a brain, a cortex, and I'm going to interchange HTM, which is the term for hierarchical temporal memory, which is our model of the cortex. We have a cortex or an HTM, and it interfaces to the world through a set of senses. Now, when the light or the sound comes into your senses, it's converted to patterns on axons, patterns on nerve fibers. And the fibers that carry information about light are identical to the fibers that carry information about sound and touch. So when you get this information comes into the cortex, there is no light, there is no sound, there is no touch. It is just patterns. That's it. It's dark in there, it's cold in there, well, it's not cold in there, but it's dark in there and it's quiet in there. Okay? And it's a theory of patterns. You have to think about a theory of patterns. We're going to find a couple terms here that are going to be important. And I actually didn't make up these terms, but some of you may know them already, but not everyone knows these terms. We're going to call the things in the world causes. You can think of that as, like, what was the ultimate cause of the pattern on my retina? What was the ultimate cause of the pattern on my cochlea? And it turns out in the world there's actually a hierarchy of causes at any point in time. So when you're listening to my speech, there's ideas, there's words, there's phonemes, etc. These are the causes in the world. On the right, what we want our system to do, we want our system to build a model of the world. We want it to form a set of variables, if you will, or in brain talk we say neurons, that become active when particular causes in the world are active, impinging on the senses. And the system has to discover these. It has to, on its own, build a model of the world, build representations of the causes in the world. And at any moment in time, those representations will have various activity on them. You can think of the activity of a cell firing, but you can think of it as a variable just having a high value or low value. And we call that collection of probabilities, as the probability across causes, the belief. It's an instantaneous value of a model of the world. So we have causes in the world. We want our system to discover those causes in the world, build a model of the causes in the world. And then when we have patterns coming in, we want it to form beliefs about what's going on out there at that time. Now I'm just going to state what our technology does and what brain's cortex does. This is my interpretation of this whole system here. There's 4 fundamental things that cortex does. The first, it has to discover the causes in the world. You are not born with that knowledge. No one programs it into your head. You were not born with knowledge about IBM and worlds and ThinkPads and whatever else you deal with day to day. You were not born with English or whatever language you speak. Hopefully you speak English. Yeah, so it has to discover this. It has to discover it on its own from the raw data. No one's going to put it in there. It has to build this model from its own, and it has to say, hey, what are the causes in the world? And intelligence is all about discovering causes. When we are in business, we try to discover the high-level causes of why businesses fail or succeed. When we're studying weather, we want to find the high-level causes of why weather patterns change. And science is all about discovering causes in the world. The second thing our system does, once it's built a model of the world, it can infer from novel input. Now, the input to a brain, instant to an HTM, it's always novel. You never have the same pattern coming in twice, ever. And this is impossible, statistically impossible. But you want to basically say, here's a new pattern coming in, and I want to recognize it. And I want to basically invoke my internal representation of the appropriate causes. So inferring causes from novel input. You can think of inference as just pattern recognition. The third thing is that if you have a model of the world, then the system ought to be able to predict the future. That is, it ought to say, hey, given my current state and my model, I ought to be able to predict what's happening next. And you do this. You're doing this all the time. Most of the time, you're not even conscious of it. But every time you touch something, like I'm putting my hand on this lectern, I have an expectation about what I'm going to feel. If this felt like metal or jello, or if my hand went through it, I'd be very surprised. I have expectations about what I'm going to see. I have expectations about what I'm going to hear. Because you understand English and you're listening to what I'm saying, you can predict what word is at the end of this sentence. And it just pops into your head automatically. Your brain is constantly trying to fill in. This is what Heck Nielsen was talking about. And finally, the neocortex is involved in high-level motor control. It used to be thought that there was a section of the neocortex involved in motor control. And many people no longer believe this. I don't believe it either. It's actually all of neocortex involved in motor control. Even the visual input areas of the cortex are involved in motor control. And I can go into the evidence if you want. But it is when I'm speaking now, it's my neocortex speaking. And yours is listening right now. And so it's a very high-level thing. So our systems, these HTMs and cortex, has to direct motor behavior. Now I'm going to spend most of my talk on the first 2 topics here. How does the system discover causes in the world, and how does it do inference? HTMs and cortex uses a hierarchy. You showed earlier, we saw, I think it was Dr. Edelman had a picture of the famous Feldman-Van Essen diagram showing the hierarchy of regions in the monkey. But I'm just going to encapsulate in this sort of picture here. You have a tree-shaped hierarchy, in sort of an inverted tree-shaped hierarchy of nodes. Now remember, there's a common cortical algorithm. So in this picture here, these little boxes represent little sections of cortex, if you want to think of it that way. We can think of them as columns or something like that. But it's a hierarchical structure. Information flows from region to region. And because there's a common cortical algorithm, each node, each box in this picture is doing the same thing. They're all doing the same thing. What makes the visual area visual is because that's what the eyes are connected to. And what makes the auditory area auditory is because what the ears are connected to. And what they think about, what they're processing is basically depending on where they are in the hierarchy. But they're all doing the same thing. So you have sensory data coming in at the bottom. You have some sort of belief structure coming out the top, which is what you're thinking. However, since this is a system that has all similar, all the elements are doing the same thing, beliefs are being passed from every node. Everybody's passing beliefs to everyone else. This is the term we want to use. It's sort of a probability distribution over causes. Now, nodes at the bottom of the hierarchy are looking at small parts of the input space, and they're going to be discovering small-level causes. So you think in vision, like edges and corners, things like that. And when you go higher up the hierarchy, these are larger causes, things that span more part of the input space. But you have beliefs being passed from node to node. Beliefs are being passed up the hierarchy, and then each node is actually making predictions and passing them down the hierarchy. And so it says at the top level, you say, I think I know what's going to happen next. And your bottom level, you say, this is what actually happened, so on. Now, I'm going to give you, I'm going to go into more details in a moment, but I just want to give you the top line idea of what's going on in each of these nodes. The top line idea is that they're storing sequences of patterns. The easiest way to think of sequences, the best analogy or simplest idea is think of it like a melody. You're seeing a series of patterns coming in, and you recognize, hey, this is a series of patterns I've seen through time before. And you memorize these common sequences. And what you want to pass to the guy above you in this hierarchy is not the notes of the melody, but the name of the melody. It's like you want to pass the name for this temporal structure that you've seen over and over again. And so what happens at the first level, you coalesce a bunch of spatial patterns into a sequence name. The next guy up in the hierarchy is building sequences of those sequences. And the next guy up is building sequences of sequences of sequences. And this has a couple of results. One is, as you're perceiving the world, like hearing me speak, you have this very fast-changing pattern coming at the bottom. But as you rise up the hierarchy, the changes are happening slower and slower. The concepts are slower than the speech. Similarly, it means if I take a very high-level concept like give a brain talk, it can end up turning into a 15-minute, complex pattern coming out of my mouth. Because we take a high-level pattern, you unfold it, unfold it, and unfold it. I'm now going to talk in detail about how this works. And then I'm going to show, well, in as much detail as I can. Then I'm going to show you simulations of what we're building and what we're going forward with this. So a little bit of theory and a little bit of practical implementation. So I'm going to answer, on the theory side, I'm going to answer two questions. Why does a hierarchy make a difference? And second one is, how does each node on its own discover infer causes? Because if each node is doing the same thing as the whole overall system is doing. So why does a hierarchy make a difference? There's several major reasons why a hierarchy makes a difference. The number one is that it allows for shared representations. And this is an efficiency argument. It's an efficiency in storage and in training. Many, many systems that people try to do complex inference engines, they run out of training time or they run out of memory and so on. But when you have a hierarchical representation, what you're doing is the low-level causes are shared among high-level causes. If you learn a new word, you don't have to learn new phonemes. You don't have to learn new letters. There is a shared, and it becomes very efficient. It's sort of an exponential increase in efficiency. It also means that when you train, you don't have to train over and over and over again. There's the sub-causes of any new object you're being exposed to. All the behaviors are inherited from before. And it's an efficiency argument. The second thing is, and this is a really beautiful element, but it takes a little while to sink in, is that the world has hierarchical structure to it. And the model that's created by the cortex and by HTMs also has a hierarchical structure to it. And the whole thing only works because there's hierarchical structure. And the hierarchical structure is in both space and time. Let me give you an example. Take a body. A body has spatial hierarchical structure to it. A body consists of a torso, legs, arms, and a head, for example. Each of those has, and those have a certain relationship to each other. Each of those has substructure. So my head has eyes, ears, nose, and mouth, and hair, for example. Each of those has substructure. The eye has an iris and a pupil and a lid and so on. There's structure, it's a hierarchical structure. You see that throughout the world. The laws of physics dictate this. There's temporal hierarchical structure. It's very easy to see that in something like language. But it's true in vision as well. There's correlations between things that are close in time, then further apart in time, and further apart in time, and so on. And because the world has this hierarchical structure, the causes in the world actually have hierarchical structure. Then the HTM or the cortex itself can capture that. The third thing is, and this again, this is really bringing in the work that Dilip has done. You can put all this in a Bayesian framework. And when you put it in a Bayesian framework, you can use belief propagation techniques. And essentially, it ensures that the system, you've got this big network of nodes. And you can force a set of beliefs at the bottom, which is like what happens when a sensory input comes in, like I look at something. And it very, very quickly forces all the nodes in this network to form a sort of copacetic or a belief that is consistent with the inputs. It's a single pass-through. Belief propagation, for those you know it, you don't need to be told this, but for those you may not know belief propagation, it's a relatively simple technique, but it's powerful. That essentially gets a network, a complex, very complex network of nodes to settle very rapidly. It's not even settling. It's basically one pass-through forming consistent set of beliefs. So I can put some patterns in the bottom, and in that half a second, bing, at the top, I get the output. For those, just to give you a sense, belief propagation also has a way of resolving ambiguity. This is a very, very simple example just to give you a sense for what I'm talking about. Imagine I have a network of 3 nodes in it. And the bottom left one is representing sounds. So just take it for a moment that it's some sounds coming in, and it's formed a belief. He says, see, it sounds 80% like the woof of a dog and 20% like the meow of a cat. And then on the bottom right one, we have a node which is representing perhaps visual input and saying, you know what, I think it's 70% the image of a pig and 30% the image of a cat. Then the next node up, the parent of this one, forms with almost certainty it's a cat, because it's the only thing that's consistent with its inputs, what it's seen in the past. So it resolves ambiguity very, very rapidly. And that's one of the things belief propagation does. The little box labeled CPT is a conditional probability table, which is all part of this Bayesian framework. And I won't go into it, but that is a very large sparse matrix, and you can think of it as synaptic trees. The last thing that the hierarchy does is it forms a mechanism for attention. You heard the importance of that earlier. You need to be able to attend to things. You can do this all the time. When I look at a visual scene, I can take in the whole scene, or I can focus on some small part of it, or I can attend to some part off to the side. When I'm listening, I can attend to part of a particular voice or not. When I'm touching things, I can attend to what's in my left hand or my right hand. You need an attentional mechanism. The hierarchy provides a very easy way of doing this. You can see here, essentially, since you have these links going up the hierarchy, you can enable some and disable some. If I enable some, that is what I'll form percepts at the top of the hierarchy about. I can limit the part of it. I can say, look, I get this big input, but I only want to pay attention to that face right there. And that's what I'll perceive at the top of the hierarchy. By the way, these connections in cortex, these are thalamocortical loops, the specific thalamocortical loops, and there's a gating function there for those of you who are interested in that. OK, now I'm going to go on to the next thing. How does each node discover causes? What is the process by which each node does its duty here? And remember what a cause is. A cause is just a persistent and reoccurring pattern. It's a persistent and reoccurring pattern in the world. We can think of it as a car or a dog or a cat, but it's a persistent and reoccurring pattern. And so there's only two types of patterns. There's common spatial patterns and there's temporal patterns. And essentially what each little section of cortex is doing, what a column is doing, I'll argue, is basically doing these two functions. It's looking for spatial patterns, common spatial patterns, and common temporal patterns. Let me walk you through a simple example of this. Let's start off with common spatial patterns. If I were to say, two things happen at the same time. This thing happens and this thing happens, and they happen at the same time. Well, then I could logically say they probably have a common cause. If they occur at the same time, then they probably have a common cause out there in the world. And I will want to remember that. And I want to assign that to a cause. I'll say that is something I want to pay attention to. That's just a spatial pattern. Let's look at a very simple example from vision. Imagine I had a little visual input, and it had 16 pixels, a 4x4 pixel patch. And that's what these little pictures are showing here. Now, your node in this cortex, your little section of cortex, your little node in HTM, you don't know what this pattern means. You don't even know it's supposed to be arrayed like this. You just have 16 numbers you're looking at, right? You and I can put it like this so you can interpret it, but it doesn't know that. And it says, look, sometimes I get patterns that occur over and over again. And the top row are patterns you might see often, that you and I would say, oh, those are lines and corners, right? It doesn't know that. It just says these patterns occur regularly together. I'm going to remember them. The row below that shows patterns which might not occur very often and may never occur. And you don't want to remember those. Those are not common spatial patterns. So you remember the common spatial patterns. You can think of this in V1, sort of like edge detection and corner detection, and so on. The next step you want to do is you want to learn common sequences. Again, if A follows B, often enough, I can assume that they have a common cause between that sequence, AB or ABC, or the notes in a melody, and so on. And what you want to do is you want to learn the common sequences of spatial patterns. So this picture will give you the sense of this. This is now, we're looking at the sequence of spatial patterns left to right through time. So the top row represents a common sequence you might see. You and I would say, oh, that's a line moving from left to right. Right? It doesn't know that. All the little node in HTM knows is like, well, this is a pattern I see over and over again. And so but we'll say that's a line moving from left to right. The next one down, you could say, oh, that's a corner moving from upper left to lower right. Again, it doesn't know that. It's just saying that's a common sequence I've seen. The pattern on the bottom would be very rarely seen or ever seen. It's just not something that's going to happen in nature, so we're not going to remember that. Now, in actuality, when we do this technically, it's a lot harder than this because you're working with these large probability distributions and messy data. But this gives you the flavor of how this works. There's another point I'm just putting in for completeness, is that for this system to work, you really have to have this context coming down from above. And I'm not going to talk about it more right now. But there is a sort of the information passing down can also help the nodes learn what's a cause and what's not a cause. Now, I'm going to switch to here to sort of, does this really work? Can you actually build these things? And I'm going to again show the work of Dilip here. And what he does, he basically said, let's try to build this in a small visual system. And so we did that. And just to test out the theory. This is not to build a system. This is not something you're going to put in your kitchen or anything like that. But we had a 32 by 32 pixel image. And we're going to look at a little line drawing in this 32 by 32 space. And we built a 3-level HTM hierarchy. Now, the bottom level, you have 64 nodes. Each is looking at a 4 by 4 pixel patch. Notice nobody looks at the whole thing. Nobody's looking at this thing, right? Everyone's looking at a little patch. Now, the next level up, there's 16 nodes, each looking at the outputs of 4 nodes below it. And remember, what they're doing is they're seeing sequences and passing the causes up and so on. And at the top of it, we have a node which is looking at the 16 from the bottom, from the middle layer. Now, there's nothing special about this hierarchical arrangement. I could put more levels, I can have more nodes, I can have fewer nodes. It really doesn't matter. The system is really robust. It's very, very, basically it'll work no matter how you hook it up almost. It has, as long as you have a hierarchy to it. What we then did is trained it on a bunch of symbols. We did a couple experiments, one of about 80, one of about 50 symbols. These are little line drawings. They don't mean too much. But interesting, the way you train it is you take one of these symbols and you have to move it through time. You have to essentially like move it across the retina of this thing. You have to be trained on moving images. The theory says you have to do that. It'd be like a child picking up an object and saying, okay, here's an apple. They have to move it around in their hand, or they have to move relative to it, or it has to move relative to them. The theory shows you cannot learn to form representations of the causes of the world if you don't use time. The way the system works, on the left here side, we show some images we trained on. You can see the helicopter, the dog, and the bee, we call it. And then we show a bunch of these. We move them around. And then we show some patterns it never saw before. So the next 2 columns over are patterns that were input that it basically said, hey, that's the same category as the previous thing. Now, it's not doing pattern matching. There is no template stored in the system. There is nowhere in this system where we stored what the training patterns look like. It's all a distributed hierarchical representation. We're not doing pattern transformations. We're not doing any kind of transformation of these things. There is no template. But basically what we're saying is I've trained it on some patterns that move through time, and then I show it a new pattern, and it says, I think that belongs to the same category as the previous one I discovered. The 4th column over shows some input patterns that were not correctly recognized, but you'll see on the 5th column over what they were classified as. So you might be able to forgive it. Here's what it looks like when you actually run this thing. What you do is you give it a pattern. On the left, you see there's a dog which has got a bunch of holes in its head. It's missing a tail and a leg. And then you pass it into this thing, and you get back out as a distribution or a set of probabilities over what it thinks it is. In this case, it says, I'm really certain it's a dog. That's my number 1 choice. And so we're showing little pictures down there to help you figure out what it's talking about. The next thing it says, well, it might be a cat, but much, much, much less probable that it's a cat. And you can see why. The little cat symbol is embedded in the dog symbol, as is all the other 3 in the top 5 there. But you get back this sort of distribution of beliefs. Here's the page which shows, these are all symbols that were recognized, classified correctly by the system. And I just want to walk through this a little bit. On the left side column, you see the dog. Notice it sees dogs facing left and facing right. And it classifies them as the same. How does it do that? Did we put in an inversion transform? Or no, we didn't do that. We just showed it dogs facing left, and we showed it dogs facing right. And we moved them around on its retina. And it says, OK, those are the same thing. And we don't have to consciously program in any kind of transformations in the system. It just handles it properly. You notice that the dogs can be different sizes, different locations. They can have a lot of noise in them. Look at the 6th column over. This is the thing we call the mug. And go down to the last row. So the 6th column over the last row. And you see a very noisy-looking mug there. You and I can see that, oh, that's a mug. But if you actually look at the data and say, well, how would you know? There's no straight lines in that thing. There's no corners. There's no obvious. If you try to program what a mug is, it would fail. It's very, very hard to say how it does. I can tell you how it works, but you can't just say this is what the definition of mug is. You don't program it. You just say show lots of pictures, and this system is very robust. It's amazingly so. As far as we know, it's the best performance of any system like this. I don't think anything comes close to it. Now, we didn't try to do a real-world problem here. We just basically said, hey, let's see if we can work on this sort of simple problem. But this is, as far as I can tell, an unsolved problem. And the way we're doing it is derived from a very accurate biological theory, and we are certain it can scale. We understand it well enough that it can scale. Let me tell you now, the remaining part of my talk, I'm going to tell you about what Numenta is doing. I'm not doing this because I'm trying to sell anything, but I think it's important scientifically, and I think some of you may be interested in this. So first thing is we're doing, we are taking what was a biological theory that I wrote about in my book, and we're turning it into a much more a computational theory. So my book came out on intelligence. There is a white paper, which I've been working on for months, which is posted today for the first time. So if you like my talk and you want the extended version of it, you can go to Numenta.com. There's a link on the front page. You can get the PDF. And it has a much more in-depth version of the talk I'm giving right now. And I'm also working on a biological mapping paper, which really goes into very, very detail about how the different components of HTM theory map to cortex and thalamus. And it gets pretty specific. down to the different cell types and different layers and the different types of loops of the thalamus and so on. But that's not our product, of course. The product is we're really developing a platform for HTM applications. We're trying to essentially build a tool set that a lot of people can use. We think we're onto something, and we think there's going to be a lot of people wanting to work on this. Actually, I know that already because a lot of them have contacted us. They've read my book and figured out what we're working on. So we're building a platform, and the goal of this platform is to have a community of developers working on it. I'll tell you a little about the platform. Here's just an architectural picture of it. There's a set of tools on the left here that let you configure HTMs, configure these hierarchies, interface them to various sorts of sensory systems, and debug them. There's a runtime environment, which is essentially a large message passing system that handles large inference engines, or Bayesian networks, if you will, and that basically run this hierarchical nodal memory architecture. It's designed to run on multiple processors and multiple servers, so we think we're going to have to build big machines, although we can run it on the examples I gave you earlier were done on a single CPU. But when we start scaling these things up, we're certain they're going to get quite large. So we're building this sort of runtime environment. It's very flexible. People can plug in new tools. They can plug in new learning algorithms in the nodes, et cetera. The tools are written in C++, but all the interfaces are done in Python, so it allows people to be very flexible in scripting. It's Linux-based, but we're using it on Macs today, but we have some interest in people using it with Windows as well. We are really trying to build a community of developers. There are thousands of people who have expressed interest in what we're doing here. There's quite a few number of people who have read my book and are interested in this, mostly corporate researchers. We've been contacted by 6 major car companies, people in geophysics and other areas. All over the map, lots of different applications. We have started working with a handful of them early. We have an early partner program. We had our first meeting in February. We're having our second meeting at the end of this month. They're going to get early versions of these tools. We don't believe that the beta version of the tools will be available before the end of the year. It might be the end of the year, it might be the beginning of 2007. But we plan to be very, very open about this. We're going to put all this stuff out there. We're going to make it as open as we can in the context of a business, of course. The third thing we're doing at Numenta, and we're doing this to test our own tools. We need to do our own test bed. So we said, let's build a really robust vision system. See if we can do that. That's a test of the theory and a test of our tools. We're pretty confident we can do this because we understand it well enough, theoretically, that we're pretty confident we're going to be able to do this. We don't know if this is going to be just something we give away or something we sell or whatever, but we're working on it. We decided to do foods for starters. And we've collected a database of, we have to have realistic images of foods, and we have to be able to maneuver them through time, like if you were manipulating them in your hands. And so we're doing this with computer-generated images, and we're having people create these, and we're creating these movies of visual objects. And we're going to start with foods, as I said. There's a well-known vision researcher who proposed the grand DARPA challenge for computer vision. He says, if we could just have a system that could always tell a cat from a dog, that would be the big prize. We're going to try to do a lot better than that. We're going to try to do apples and pears and oranges and 50 or 100 other different fruits and foods and so on. Let me just tell you a little bit about what we think this technology can be used for. First of all, the easiest thing to do is say, well, it can be used for things that humans find easy to do and computers find hard to do, such as visual inference or such as robotics and so on. And so those are the obvious things to do, sort of classic AI things. And there's many applications there, from security systems, like why do we have people looking at video cameras all day long saying, is anyone breaking in? Is anyone breaking in? No. Why don't we have a system do that? Self-driving cars, et cetera. And of course, you could extend that with new sensors. There's no reason we have to work with the kind of sensors humans have. As long as they have certain set of properties, which I could elaborate, you could do it with infrared and sonar and radar and something like that. And then the next thing you can do, beyond sort of the classic AI problems, and I think this is where most of the interesting action is going to be. So when I think about cognitive computing, I don't think about building robots. I don't think about building machines that look and emulate humans. I think about machines that work on the principles of cortex that do really amazing other stuff that humans are not good at. And that's where the action is going to take place, in my opinion. I'll give you some examples here. Take for example, weather. This is an example I use in my book. We have weather stations all around this country. Each weather station is detecting a few local properties of weather, such as temperature, wind, atmospheric pressure, and precipitation. That collection of sensors is very analogous to a retina. You're essentially taking little samples in a topological grid, a two-dimensional grid. You're sampling local properties. You can take that information and feed it into an HTM. And it will perceive weather the way you and I perceive visual scenes. It'll be a weather brain. It'll think about weather. And the goal of that system is to discover high-level causes. What are the high-level causes? Well, firstly, storm fronts, we know about those. And then you have big storms like hurricanes, and you have things like the jet stream. And then take something like El Nino. El Nino is a very high-level cause. It persists over a very large area in long periods of time. And it was only 25 years ago we discovered that. But that's basically what the science of weather is, discovering the high-level causes and then using that to predict the future. HTMs can do that directly. You can do the same thing with geology. We've been approached by people who have underground geophysical data, three-dimensional geophysical data, and they don't know how to interpret it. They don't know where to look, how to figure out what are the causes underlying here. Where will I find oil, where I won't find oil, things like that. People want to apply this to markets. Markets are these sort of hierarchically structured, and I can explain what I mean by that, but hierarchically structured data sets, and you want to discover the causes in them and so on. I believe you can apply this to many, many problems that humans have trouble with in mathematics and physics. And I think this is going to be actually over time, not early on, but over time. There will be a real boon to our scientific discovery processes. Let me just review here. I'm getting close to wrapping up. The four capabilities of what I believe Cortex is doing, what HTM is doing, is discovering causes. That's the number one thing. Figuring out what's out in the world on its own through sensory data. Building a model of the world. And the better that model is, the smarter you are, and the smarter the system is. Doing inference on novel inputs. Doing prediction and behavior, which I did not talk about in depth here, but the theory actually explains this. We can understand how the cortex generates behavior. Now, the thing I find exciting is you can go beyond biology. First of all, there's no doubt in my mind we can make these systems run faster than brains. Brains are made of very slow elements. I said that to begin with. I don't see any reason why eventually we can't make our artificial cortexes run 1,000,000 times faster. And think 1,000,000 times faster. And I got to believe that's going to be a good thing. We can make them larger. Think about a really great brain, like Einstein's brain or something. I know Einstein was a smart guy. We can all admit that. I think he thought of things other people didn't think about. His brain worked on the same principle your and my brain worked on. He didn't have a different brain. He didn't work on some relativistic Einsteinian principles. It worked just like yours and ours. But he clearly was a little bit different. And I don't know what the differences was. Maybe he had more material, maybe he had more connections, maybe he had broader connections. Who knows? The point was it was a small variation on a population of brains. It wasn't even a large variation. It was a small genetic variation, and it was enough to make that guy really smart. And we can do the same thing here. We can experiment and say, how big can we make this stuff? Is humans the limit? I doubt it. We can also do things that have normal brains. People who have, savants who have the ability to memorize lots of detail but not generalize well. We should be able to do that as well. So there's a lot of variations here. We should be able to make these things bigger and more capable. And finally, the one I mentioned earlier was exotic senses. I'm really excited about this because essentially when you realize what this technology can do, you can apply it to almost a huge number of problems. There are so many things in the world we don't understand, or we do understand, we can't, humans are not good at perceiving or understanding or doing inference on. And these systems ought to be capably designed to do that. And so, whether it's weather or, other things like that, there's a tremendous number of possibilities in the exotic senses. So that's the basic capabilities of the system. If I were to spin our spinner to, before I do that, if you want more information, you can read my book. Get out of the library here. I hope they have it. You go to the website, you put your name on our email distribution list. We've only sent out 3 emails in the last 9 months, so you're not going to get swamped from us. But there's going to go out one that's going to go out this week announcing the white paper. The white paper is already there. So if I were to spin the spinner today, this is how it looks when I walk in the office. I'm pretty confident about this. Time will tell. I'm not asking you guys to believe me or not. Some people get what we're doing. Some people don't. Some people are excited about it. Some people aren't. But we have a lot of interest in what we're doing. We're confident we can build these machines. We're confident we can do the things I just talked about. And that's our plan. And we're trying to build a community of people. So if you're interested, we'd love to work with you. And that's the end of my talk. Thank you. I have one of the microphones. I'll give it. You're supposed to take that around.
Yes, questions. Please, Joaquin.
Thanks, Dr. Hawkins, for this very beautiful presentation. I must say right off that your scheme, your model, is extremely friendly to cortical physiology, especially in its hierarchical aspects. And I hope to be able to sketch some of it tomorrow. Now, I would like to make a couple of specific comments, however. In order to unpack a unit of temporally defined sequence or gestalt in the form of behavior, reasoning, or language, your system, certainly the brain, needs two elements. One is working memory in order to mediate cross-temporal contingencies. I'm sure you would agree with that. And second, you need an agency, as we have in the brain, like the prefrontal cortex, that allows the enactment of those sequences from a plan toward a goal. Would you agree with these two comments?
I would agree. I hope everyone heard those comments, so I don't have to repeat them. Did everyone hear those? Yeah, I would agree with that. I would agree with that. I don't know if you want me to elaborate on that.
In what way have you introduced, for instance, working memory in your system?
So any model, the question is, have we implemented working memory in our system? In any model, you have to make a decision how far down you want to go, emulating the accuracy of the biology, for example. So for example, in our model, we stop at certain points. We don't model ion channels. Okay, that's not there. And so we make certain. We say, okay, we think we can stop here. When it comes to working memory, there's a lot known about working memory in the neocortex. And I'm a fan of your work, so I'm happy you're here. I've read most of your stuff, or a lot of stuff. I shouldn't say most of it. But anyway, there's a lot of knowledge about working memory and a lot of hypotheses about the biological and physiological mechanisms underlying it. We don't try to capture them. But when we build this in a computer-based system and software, it's very simple to implement working memory. You just have variables that persist. And it becomes an easier process for us. So we don't have to work on it as hard, perhaps, as a biological piece of tissue does, where the idea of working memory in a piece of biological tissue might be actually hard because biology just doesn't have those sort of persistent states that we easily can do in technology. So we haven't really called it out, per se, in our model, saying, oh, here's the working memory aspect of it. But these beliefs, we can freeze them or not freeze them. We can hold them. They stay there as long as we want. We don't have to build some special mechanism for it. So I believe my answer is a bit weak to your question, because I imagine over time we'll have to do more. We have focused most of our efforts on figuring out how we do basic sensory perception, forming persistent beliefs of causes in the world, and we haven't gotten into great detail about the generation of complex patterns. The theory explains that. And in fact, in my book, I wrote a fair amount about how it is that a high-level percept gets played out over time, relative to your first question, and in what are the motivations for that, and so on. But be honestly, what we've done so far, we said, what are we going to bite off so far? We said, okay, what we're really going to focus on is this sort of basic inference of spatial temporal patterns coming in, and it has allowed us the luxury of not addressing some of the more difficulties I think we're going to get to if we think about prefrontal cortex. Which, you pick what you're going to work on first. Thank you for your comments.
I have a Trio 600, and I'm very happy with it. But
we're not doing tech support today, so
you're following the ideas, the theories of Hubel and Wiesel in a hierarchical model, whereas it's been shown by Semir Zeki in his papers on chronoarchitectonics that model is bad. It isn't in the brain. And you're talking about top-down, essentially. There's no evidence for that either. So I think that you're not physiological.
Okay, so the
question... Stick with the trio.
Stick with the trio. You're basically telling me to go... You're telling me to go home. Well, thanks. That's a very different kind of contrary comment I had before. I would argue just the opposite. It is really physiological. And you say there's no evidence for top-down. There is tremendous evidence for top-down. I can tell you the connections from layer 6 to layer 1 going back down the cortex. They're not going up through the thalamus. They go back down directly, region to region. It's there. Now, there's a lot of neuroscientists who just want to ignore that stuff. But there's a tremendous amount of connections going backwards, and you can't ignore it. So, and then in terms of the Hubel and Wiesel comment, look, the idea of a hierarchical memory system is not new. Right? No one's done it. The idea of doing Bayesian stuff is not new. The idea of doing prediction in temporal memory, none of this is new. I'm not pretending I invented anything new here. But it really matters, the ingredients you put them together and how you do it. It makes a big difference. Going back to my computer world, which you want me to return to. The Palm Pilot had nothing new in it. There was nothing new in that product. It was very, very successful because you just had to know what was the right set of ingredients out of 1,000. Which 5 do you have to put together? Which are the right ones and which are the wrong ones? And that's how I feel about this theory, too. This is new in the sense of the way we do it. Most people would contrast this to sort of Bayesian models. And I say, you know what? We do some very unique things here. How we handle time, how we handle the memory in time, how we discover causes. This stuff, Hubel and Wiesel didn't have any of this stuff. And so to say that, oh, this is like a Hubel and Wiesel model, it's not true. I mean, you can say that, but I think it belies a sort of lack of depth, at least understanding what I'm doing, and perhaps an overextension of what they did. I'm not trying to take anything away from anybody. I don't care. I'd be happy if someone else invented this. I don't care. I'm just trying to solve a problem. I'm interested in this. I want to understand how it works. I want to build things working on it, and I think we can do it. And if you don't want to believe in it, that's fine. I don't care. I'm going to work on it, and time will tell if I'm right, you know?
Yes, here.
Hey, Jeff, you mentioned the thalamocortical loops, but you didn't, you just sort of mentioned it. You didn't really describe what goes from the thalamus to the cortex and what comes back from the cortex to the thalamus. Is that a central issue in your modules here, or is that sort of subsumed within the modules?
I'll just describe it. I told you I wasn't going to do a biological talk, but there's 2 types of loops between the thalamus and the cortex. There's one that's called like the specific pathways, which would be like the pulvinar, LGN, and so on. And those are very sort of topographic. They're sort of relay cells, if you want to call them that way, and they're gated. So you have these sort of bimodal cells. In our model, the up pathway, and it's been argued that people like Sherman and Guillory have argued that the up pathway is not cortical to cortical, but it's cortical thalamical cortical. And I buy that. That's the primary up pathway. That is an attentional mechanism in my model. That's the ability, the thalamus is sitting there saying, and you look at the inputs to the thalamus, so those relay cells, there's basically a top-down attentional mechanism and a bottom-up, and I can explain why those are, and the reticular nucleus, what it's doing in that role. There's another loop through the thalamus. This is called the nonspecific or the matrix, some people call it that. And these are more diffuse. They basically come from layer 5 cells. They go to these matrix cells in the thalamus and back up into layer 1 and 2. So maybe you know these things. Not many people do. So that, I have speculated, and I believe, is a timing mechanism, because the theory shows that in some sensory modalities, you have to store relative or specific time. And you need to do it in a global way. And there's no other circuit in the cortex and the thalamus that I can think that could play the proper role. And that one has a beautiful topology for it. And I've talked to many thalamic experts about whether they've measured the physiological properties. Well, there's only a few, actually. Maybe you're one of them, I missed you. But talked to a number of thalamic experts if they've measured the physiological properties of those cells, because I think they ought to be sort of unique, the matrix thalamic cells. And apparently, I've not found anyone who's ever measured those. So the theory talks a lot about that. And in our current model, we are not modeling the second loop. We're not modeling the timing loop. It turns out you don't really need it as much in like vision and certain other problems.
You mentioned that the upward path is from the cortex to the thalamus and then back to the cortex?
Yes.
Good.
Yeah, there's a direct connection as well. I don't want to lose the non-neuroscience people here, but I'm maybe establishing some credibility. There's a direct cortical connection, which is really what Feldman and Van Essen mapped out in that diagram. But the argument has been made that that is a weaker one. And I believe they're actually playing the same purpose. Nature isn't perfect. So there's a direct one, and there's one through the thalamus, and I think the one through the thalamus is intentional. Should we take one more question?
Yeah, well, maybe a couple more, but I sat up in the back, and I know the people in the back never got called. Is there anybody up there who has a question? There, right up there.
Right in the back there.
And then we'll come back.
Shout it out. I'll repeat your question. Oh, well, they want to get you on a mic.
A comment first, Jeff.
Oh, a comment. Huh? Be kind, please.
Well, maybe two comments. One comment is I applaud your bravery in coming and presenting this theory that may or may not have worked out all the, responded to all the critiques in neuroscience. But the second observation was the pattern recognition examples that you gave sound suspiciously similar to neural networks of 20 years ago. The question I had for you regarding the hierarchical temporal memory is, how do you handle issues of, there are lots of other cognition acts that I don't know how you would explain it using this model, particularly relating to skill memory and also functional aspects of tasks that you do. And even as simple as the grouping tasks prior to your recognition example, how would you explain that in your model?
What's a grouping task?
The fact that there is an object there in the first place.
Okay, so I didn't hear your criticisms in the beginning, so I won't respond to them. Maybe I heard one, is that isn't this just a neural network? The brain is a neural network. But if you go back and you look at the history of neural networks, and believe me, I'm old enough to be there, okay? Neural networks is this term that is a large class of problems. And so you can't put them all in one category. The vast majority of neural networks that were proposed and have been worked on do not have really any sort of biological relevance other than, quote, they have neurons. But there's no higher level structure involved. They had no cognizance of all the different sort of parts of the neocortex and thalamus are doing. They had most of them had a very poor sense of time. They were mostly static classifiers of various sorts. And so I'm not here to ding neural networks, but to say that, boy, isn't this just a neural network? No, it's certainly not a network anyone I've ever heard about before. Now, the question about how does it even, I think your question about grouping, how does it do that? You know what? If you didn't get it from the talk, I'm just not going to be able to do it here. You can read the paper, but that's the whole point of this thing. The thing is, it's trying to group together inference. Pattern recognition is a many-to-one problem. It's basically saying, I have a gazillion patterns out here that I want to put in one category, and a gazillion patterns out here I want to put in another category, and how do I do that? And the only way the brain has to work with is basically coincidence in time and sequences in time. That's it. And you do this in a hierarchy in the way I just described it here. It actually ends up building at the top, and I didn't give all the details on it, but it ends up building at the top representations for those causes. It actually forms those groups. And I'd be glad to speak to you further about it, explain, maybe try to get over whatever I didn't explain well here. But that's the whole point of the theory. The point that does that, and I think we've shown that it does that. And it does it in the way I described. You just take these patterns, you move around. It has to do it that way. So I'm sorry if I didn't work in that regard, but best I can.
You did show good attention by not hearing the first part of her statement.
Oh, yes.
So that was, you suppressed that.
Yes.
Right here. Right there? Right here? Yeah.
I think he's waiting for a microphone.
Another one up, that gentleman.
I really liked your talk as
Thank
a
you.
neuroscientist.
Thank you.
And I have a question about another loop circuit that I think might be interesting to it, which is the striatal loop circuit with neocortex. You've got these thalamico-cortical loops, and you've got two of them. And then you have striatum, which has these glutamatergic reciprocal loops, which seem to me must also be playing a critical role, and I wonder if you have any thoughts on that.
I wish I did. I don't. I don't. So there's not just the striatum. You also got basal ganglia, and flowing back through the thalamus as well. There's a whole bunch of these other things going on, and I really don't have a good explanation for that. And I'm not an expert in it, and I apologize for that. I don't even have a hypothesis on the striatum. I do have an overall philosophy about how the circuitry I just detailed relates to the rest of the brain, and maybe I'll offer that to you. Imagine if we could just isolate the thalamocortical circuit, and maybe it works like the way I said. The rest of the world is out there, right? And the rest of the world includes your body and other parts of the nervous system, right? So the other parts of the nervous system are just parts of the world out there. And the neocortex has to learn about them. And it has to learn what they do. And it has to form basically representations of the behavior of other parts of the brain. So let me give you a flavor for how I think motor control comes about. you have a lot of non-cortical, subcortical motor behavior, basically walking and chewing and arm retraction, and all, breathing and sneezing, all this stuff you do, which is non-cortical. The neocortex is sitting up there, and it's watching this through the proprioceptive system and through your external sensors or whatever. And it basically says, oh, that's a sneeze, I know what that is, or a cough, I know what that is. I've seen it before. It's a pattern. I'm going to form a representation for it. It's a cause in the world. And so now it has an internal representation of something like walking or something like arm retraction. It then sends fibers from these basic layer 5 cells down, and it does an auto-associative link to whatever, it has to go in the right direction. It's not going to work. But basically it says, okay, maybe I'm sending this signal down to the basal ganglia, or maybe I'm sending it down to the brainstem or whatever. And it's got sort of a pure sort of Hebbian auto-associative linking saying, okay, well, when the activity for walking, there's some cells that are generating that subcortically. When they're active, and my representation active, I'll make that link. So now when the cortex actually imagines or thinks or predicts behavior like walking, it can make the walking happen. It's like I can now control my breathing. I can control my walking, but most of the time I don't have to. My cortex can take it over. So I have this sort of very naive, well, it's not naive, that I believe is true. But things like the striatum or other parts of the subcortical stuff, I kind of just say, you know what, I'm going to throw them all over there into this other part of the world. It's going to try to model it, it's going to try to react with it, and it's going to form these sort of auto-associative links. And it's the best I can do for you right now. We do have a better theory about how the interaction between the hippocampus and the cortex works, because that's a much more closer link. But things like the striatum I'm really ignorant about, and I apologize for
One
that.
more question up there.
Hi, Jeff.
Hi.
Let me end with an engineering question. What could you comment about implementation issues that arise because of the need for massive interconnect? So how do you see it placing limits on size of the system and solving real-world problems?
The question is, what are the kind of engineering constraints we're going to run into as we build these systems? So like the message interconnects.
Especially the interconnects.
Yeah. So look, we are doing our best at this right now. We're guessing. So we're building this system. We really don't know yet. We've got it running on these simple, small multiprocessor systems. But we really don't know yet what bottlenecks we're going to run into when we run them in large clusters. And we're bringing up our first large cluster now. So there's a lot of engineering questions which we're worried about, but we don't know the answers to yet. The best analogy I can make, and I like this analogy, is if you go back 50 years ago or 60 years ago when they were building the first digital computers, they didn't know diddly squat about this stuff. They had the basic theory, Turing theory and that kind of thing, but they didn't know about compilers and disk drives and debuggers, and they didn't know about caching and none of this stuff, right? And they started building stuff, and it was slow, and it was cumbersome, and they had to figure it out. Well, that's kind of where we are. We're at that stage right now. We're building I think the ENIAC of cortical machines, if you will. What was IBM's first one? I'm sorry, I wish I knew that. But we're building this early one, and there's just a ton of stuff like that we will just not know until we start building it. This is why our approach is going to be as open as possible. If I want Numenta to survive, I just have to let, we have to, as Guy Kawasaki would say, let 1,000 flowers bloom. We can't we're not going to figure this all out. We have to let other people experiment with this, other people attempt these things, other people figure out what works and what doesn't work and how to improve these algorithms. So if you're interested, we're interested in working with you, but we're really going to be ready at the end of the year, but we're kind of busy right now. So thank you very much again.
Thank you, Jeff. And we'd like everybody to reassemble at 3 o'clock, so take a little break.